This is section 2.8. This is related rates. These are word problems. Okay. Now, related rates is really all about the chain rule. You can think of it in terms of implicit differentiation. It's kind of the same thing. So I just want to review some of the chain rule stuff with you, in particular the notation, because I think it's going to be insightful. So when you have a function with another function inside of it, this is called the composition of two functions, right? When you take the derivative, we saw if we use functional notation, it looks something like this. Take the derivative of the outside, you keep the inside, multiply by the derivative of the inside. Now, this is what I call a functional notation approach. But we also learned something called Leibniz notation. So with Leibniz notation, the way that worked is you wrote something like, if you wanted, let's call it df dx, so you're differentiating the function f. What you first do is you take the derivative of the outside, but you treat the inside thing as a variable. So sometimes we would write this as df dg. And this means the outside function is f, you're treating g as a variable. So when you take the derivative, the net effect is you keep the inside. And then you got to multiply by the derivative of the inside. So the derivative of the inside is dg dx, like this. Okay. And the nice thing about this notation is that it kind of looks like the differentials dg cancel out. We actually worked with u substitution before. So when we did u substitution, we kind of wrote it as df du times du dx. So we kind of we let u be the substitution. And then when you do your substitution, it's like you have your f of u, and this would be your du part. Okay. So I think thinking of things in this way with this Leibniz notation is really going to make our related rates word problems work pretty easily. And why don't we take a look at the worksheet? I didn't make a video of it for some reason. I don't remember why. Or maybe I did and I lost it. I don't know, but we're dealing with rates. And anytime you're dealing with rates, it's one quantity changing with respect to another quantity. And the rates that we're going to be looking at primarily is you're going to have some quantity. The bottom quantity is going to be time. So really time is our independent variable. Okay. So in many real world applications, related quantities are changing with respect to time. Oops, I'm going to do this in black, sorry. And we have an example, right? Excuse me. I'm sorry, hold on. So for example, if we have this situation of inflating a balloon being filled with air, we could say that the rate of change in the volume, so the way I'd write the rate of change in the volume is I write that as dV dt, is related to the rate of change in the radius. And the rate of change in the radius is dr dt. So what do I mean by that? Let's say you're blowing up a balloon. So you have your balloon's really small, and then it gets bigger, and then it gets bigger, and then it gets bigger, right? As you're inflating this balloon, it's 3D. So maybe I'll go like this. And as you're inflating this balloon, not only is the volume changing, in other words, the amount of air inside the balloon is getting bigger and bigger, but the radius, the distance from the center to the edge, is also getting bigger. So that little radius piece is getting longer. And in this case, we're going to say that dv dt and dr dt are related rates. And they're related because the volume is related to r. Okay. So I want to do several things here. I want to both help you reason through an example, and then I want to generalize the process of what we're doing down here. So let's figure out how to do that. A big part of what we'll be doing this week is reading these examples carefully through and really unpacking the different pieces of information